demonstrates how the infant rats are treated.
Okay, what we have here is normal active maternal behavior. She's retrieving the pups as you see. We've disturbed her nest, so she's going to gather them back into a ball, lick and stimulate each one in turn, and rather actively and rotate among them sporadically for a short period of time. Eventually, in 5 or 10 minutes, she'll settle back over them and simply crouch over them so that they can suckle. What we have here are pups who have been away from the mom for about 2 hours. They've had a temporary deprivation of maternal touch. When I stimulate them with this brush, with this very robust pattern, it simulates, we think, how she behaves when she licks them and stimulates them and retrieves them. The longer really they're separated from the mom, we have found, the less responsive they are, which is again another sign probably of the deprivation. But we don't do it at all gently, because she doesn't do it at all gently. And it takes stimulation this active to return their enzymes to normal.
It's an interesting thought, but one can say here that the need for a mother's touch is really brain-based. It isn't just nice to have it. It's a requirement for the normal development and growth of the baby.
With all this research in mind, you might wonder if lack of affection can actually stunt the growth of human children. Unfortunately, the answer is yes. John Bowlby and Renee Spitz conducted a study of institutionalized youngsters who were emotionally deprived. Although the children were well fed and received good medical care, their rate of growth was significantly below the normal range for their age groups. Because physical growth is clearly affected by psychological experience, this phenomenon is known as psychosocial dwarfism. The mechanism by which this emotional deprivation stunted the children's growth seems to be the failure of the brain's hypothalamus, which normally stimulates the pituitary gland to secrete growth hormones. So the lack of touching may have had the same effect as it did with the baby rats, reducing the production of biochemical substances essential for growth. But whenever children are placed with a loving family, they begin to return to normal size. In one study, these children who had been emotionally deprived caught up with their peers by growing an average of nearly 8 inches in a year. The normal growth for that period is only 2.5 inches. So it's clear that the functioning of the brain can be altered by behavior and by the social environment. But what about its very structure? One of the first attempts to demonstrate permanent alterations in the structure of the brain came in a series of studies at the University of California at Berkeley. A research team led by Mark Rosenzweig studied the effects of raising rats in an enriched, stimulating environment as compared to ordinary or impoverished environments. Not only were the enriched environment rats superior learners in adulthood, their brains were physically changed by their experience. The brains of the stimulated rats grew larger, with a thicker cortex, especially the occipital cortex, the region responsible for vision. Also, there was a greater number of certain neurotransmitters, and there were more and larger spines on the dendrites, the branch fibers of neurons which receive signals from other neurons. These sorts of physical changes in the brain can have a lifelong effect. Studies have shown, for instance, that touching newborn rats not only stimulates growth, as we've seen, but also helps them to cope better with stress throughout their lives. And this, in turn, serves to reduce the normal effects of aging, such as learning difficulties and diseases of senility. Michael Meany is a developmental psychologist at McGill University. He's investigating how early experiences can change an animal's brain and behavior. In particular, how the animal is affected by stress and the release of hormones called glucocorticoids.
When you expose any mammalian species, animal, human, to a stressful situation, there is an enormous increase in the secretion of glucocorticoids. These hormones increase the heart rate, they decrease digestion, and in general allow the organism to better be able to cope with the challenge presented by the stressor. The problem with extensive exposure to these glucocorticoids is that they can actually literally kill brain cells, specifically the glucocorticoid-sensitive neurons within the hippocampus. The hippocampus is a structure that is absolutely critical for learning and memory. And the problem that you face is that with the degeneration of hippocampal neurons in the aged animal is that you begin to see the brain less capable of processing information, and you see profound deficits in learning and memory. What we're trying to do in these experiments is to examine the ability of the animal to learn and remember events, particularly spatial events. Now, rats are proficient but reluctant swimmers. And if you put them in a pool of water, they'll use the first opportunity they can to get out of the water. When you compare the handled and non-handled animals, the older handled animals look very much like the younger animals. Within a very few number of trials, the animals are quickly able to learn where the platform is located, and it takes them very little time to swim to the platform and get out of the water. When you look at the older non-handled animals, these are the animals that show you major hippocampal cell loss. These animals take an awful long time to learn where the platform is located and show you very, very poor memory for where the platform is located. What you're looking at presented here on the monitor is a digitized version of the position of the rat and the position of the platform. What this equipment does is to give us two pieces of information. First of all, the amount of time that it takes for the animal to actually find the platform, and the distance swam by the animal prior to finding the platform. Both of these are our measures of exactly how well the animal knows the location of the platform with respect to the cues in the room. The question that we're trying to pose is that could an individual's ability to cope with stress be a factor that predicts whether or not we see intellectual impairment in individuals and how early it shows up? It's very possible that the individual differences in intellectual functioning among elderly people are really related to their ability to cope with stress. And so that in the individuals that are showing you intellectual impairments, 55, 60 years of age, that these people might be like the non-handled rats, less capable of dealing with a stressor, more likely to show you increased glucocorticoid exposure, more likely to show you loss of hippocampal cells, more likely then to show you the cognitive impairments that